Okay, so I'm going to talk about the geophysical tools that our industry uses to find water. Now these tools are not only used in looking for water, but they're used in all sorts of endeavors in geology, mining, engineering. Jobs I've done have to do with finding more sand and gravel resources. I work for 2 mining companies to help them locate where old mines were, underground mines were, so that their workers that were trying to reclaim them wouldn't be in danger. And so those were really valuable to those companies. These techniques are used for engineers that build highways, so that they can decide whether they need to, the rock's too hard to rip, or whether they need to drill and blast or rip, so it's that decision they can make, because the cost is much different. So here on the right is a picture of well driller Bob Tarbert in Lincoln County with DNR geologist Mike Hamilton. I did a job there at that site, and then the job on the left was a well that was drilled after a recommendation that I made. So I'm going to go through, talk about 3 methods. So they're called electrical resistivity, which is an imaging method with the new technology, seismic refraction, which is another imaging method, and then seismo-electric sounding. Now might mention that the refraction uses the very fast seismic wave called the compressional wave. And so I'll show you an example of just how we're using that. So the seismo-electric is a rather new technique, although it's been known for about 75 years, but it's just advanced into the mainstream use because of computer technology. Of course, all these methods benefited from microprocessors and the very rapid computer like the one I've got here. So we're going to talk about what they are, how they work, what it means, its use, and some examples. So here's the list of the different types of aquifers. They all have to do with either the basalt on the left or the granite-like, geologists call it a quartz monzonite. So we got names for all the different rocks. In many cases, these 2 rocks are substantially weathered, and in some cases they converted to soil. So those weathering characteristics have a lot to do with developing the aquifer in place. And in fact, Bob Tarbert, the well driller, gave me a lesson in what he sees in the well drilling that us geologists don't see. And so I'm going to show you an example of his discovery that I need to credit to Bob. So the first electroresistivity has to do with everything with electricity, and so does the seismo-electric. So I'm showing here a list of different rocks and the range of resistivity values. And if you see a bottle of water like this, but this one doesn't have that, it shows the conductivity of the water, which is an indication of the mineral content. And the second one is a chart of the velocities of different rocks, the velocities of how fast sound waves pass through them. These are very important for the interpretation, as are the resistivity values. So the weathered surface material would have a velocity of 1,000 feet per second that sound travels. Sound travels through granite metamorphic rocks much faster, some of it over 23,000 feet if it's buried at great depth. Next, so we'll talk about resistivity imaging first. As I mentioned, it has a lot to do with Ohm's law. And there's an interesting little diagram. So Ohm's law has to do with the relationship of current, voltage, and resistivity. And conductivity is the exact opposite of it. So this is just a general diagram how we lay out the resistivity survey. So we use a battery connected and A and B electrodes, put current in through the battery, and then it's read in the receivers on the M and N electrode. And depending upon the spacing, they apply this formula to come up with an average resistivity, and that
How big of an
resistivity.
area are you talking? You're checking.
What's that?
How big of an area?
I'll show you here in a minute. Show you a bit. So after that reading is taken, that plot point is directly under it at a 45-degree angle. So the idea is to get a lot of these readings so you can see what's underground. With just one or two, you can't tell very much. So here is a comparison of the old technique that we used before 1990, before 1985. So we had a transmitter and receiver, had 4 wires, and so here's the wires with steel stakes in the ground, and you would charge it up with the battery and then read the resistivity. Then you had to go through the hand calculations. So I did that for about 10 years, but today we have this machine which does almost all the work for us. We set it off and we can go take lunch. So what it is, we lay out a long string of electrodes. This one shows 32, some of them are over 100. So that machine keeps track of all of this. So it chooses which of the 4 electrodes to use, 2 transmitters and 2 receivers. And then it transmits the power, records the reading, and then goes to the next. And it takes about 9 seconds to do a reading and then advance to the next one. So this is what the equipment looks like. So on the left are the steel stakes, and the cable, and you see on the cable these shiny cylinders. Those are the hardwired electrodes, that I call them. And they're attached to a steel stake in the ground. And then here's the operator working on that. So here's the array of data that's recorded in 3 hours. So on one of the old surveys we did before 1980, we could only get about 12 readings a day. And so this machine is really, really valuable. So we can make good interpretations. But again, I say, it's just data, and we have to interpret what it really means. And so here's the layout with my friend Phil Moyle. So you can see the yellow cable stretched out into the trees, the superstring, the big yellow black box. So we spent about 3 days doing some work. This is for a mining company where we had to tell the mining company where there was a danger of filling in the old mine pits if it was a danger to their equipment operators. So example 1. So after the data's all in, we get an interpreted section. The software puts this together, all the data at one time, and so in about 10 seconds it does all the interpretation for us and gives us what's called a resistivity profile. So we have from 0 to 1,500 feet in length and down to 368 feet. The usual depth of investigation is about 300 feet for this method. Now this profile is like a slice through the earth. So we're looking sideways at the resistivity values. Here's the location of the line parallel to Jensen Road near Cheney. And so what it's showing us are the blue areas that are very low resistivity. So values that I use are if they're less than 80 ohm meters, so they would be blue, that's a potential water zone. So let me go to the next. So before I go there, so the red areas are very hard rock and they don't contain any water. The reason these are blue is because there's water in those zones to increase or decrease the resistivity, increase the conductivity, and so that's the information we rely on. The red areas are very hard rock, like in this area it would be a metamorphic rock. Some areas less. So there were 3 wells drilled on those 4 points. This well drilled to 140 feet, found water starting at 65, and then water again at 100 to 130, and then they tested water at 20 gallons a minute at 140 feet. So that black line, vertical line, is the bottom of the well. This one, of course, we sited these wells directly on those blue features. So they both were productive. This one was tested at 15 gallons a minute. This one tested at 15 gallons a minute also. So I still have more work to do for these folks at another location. So this is kind of a model of what the aquifer looks like. You know, I suspect that it's fractured rock, and the reason it's fractured, and that's the reason it contains the water. If you were just to drill blindly like this person did that owned this property, he drilled 2 dry holes before I got a call. I meant not to be commercial here, but that's really the way it happened. So now we drilled 2 good wells for him and a 3rd one for his neighbor. Oh, and by the way, here's a picture near Grand Coulee of what fractured rock really looks like. So if you see it, it's really obvious. So we could suspect that that rock extending at depth, once you get below the water table, would have water in it too. So I think that's the last of that one.
What size of an area can you cover accurately?
Well, the cables are set up so we can do. Oh God, sorry. I was getting way too hot. It's cold outside. There you go, Frank. Like up here. Is that good? That's good. Okay. What we can do, we can lay the cables out, record for a time, and then leapfrog and go ahead. Or we can do the same thing and do one survey along one line, move it to the side, and side again, and we can do a 3-dimensional interpretation. So there's 2-dimensional interpretation software and 3-dimensional software. For one mining company, we had to use the 3-dimensional interpretation because they had a special problem that required that. Yes?
Can you get an idea of the gallons per minute production potential for any one of those spots before drilling?
Yeah, we can estimate it. So based on the area of the blue area and the value in the resistivity. So it seems, I've plotted up a lot of those. It seems to be a fairly reasonable plus or minus 20% error in that estimate. So, okay, any other questions before we go on? Yes?
If the well water was contaminated, would that affect any of the readings? For example,
No.
California has an aquifer that's contaminated, so they have to pump
Yeah.
all the water out and go through a plant
Yeah.
to get the water back into shape, and then the water continues, the same amount of
Yeah.
water they take out, they put, goes back in.
Yeah.
And they're recycling the entire aquifer.
Well, I've not worked in a situation like that, but usually contaminated water would be give a much lower resistivity value.
Right.
And so you can actually track it if you know that.
The
And
resistivity would change.
yes, and we could do surveys on a weekly or a monthly or yearly basis to watch or track a pollution stream.
Right.
So this was done at Marshall, in fact. So we did a long period tests about every month or every 3 months. Yeah.
Is there anything similar to water and resistance thing? The reason I'm asking that is on this water panel 6-7 years ago that I was on, the Department of Water had said that, certain testing that Stephen Neubauer had talked about, well, we can't do that because it looks very much like oil and we can't tell the difference and blah, blah. So, is there anything similar, that's all I'm asking, in that kind of testing and resistance?
Yeah, there's a lot of geophysical techniques. There's
But the echo kind of thing, like a sound thing, that would be different than what you're talking about?
No, it's different than this, but I'm going to talk about seismic here coming up next.
So they were lying to us possibly,
Well, they're using seismic reflection.
okay?
It's a little different, but it gathered the same kind of information. But I don't use the large thumper trucks like they do in oil and gas. Well, I just use a sledgehammer for a source. But there's a lot of high technology involved in the oil and gas business on interpreting their seismic sections. When I was working at Standard Oil, I had my job as a geologist. I had a partner that was a geophysicist, and so his job was to know all about the geophysics. And it was almost entirely seismic reflection data. So we had,
Well, it just never
That's
made any
it.
sense to me that, well, we can't tell the difference between water and oil underground.
you really can't, but with today's technology, they can see a lot of things in the amplitudes that you couldn't see 20 years ago. And I don't follow that, so I don't know what they all are. So
How do
So-
you charge these wells? They're so isolated and raw. So just the normal
you mean
fall thing?
these right here? Well, this happens to be in a valley that's got uplands. So the water flows, the rain falls, the snow falls in the uplands, and it drains down the drainage, and then just goes underground into the fracture systems. So I really see this area as a continually renewing water resource. And so it's quite unique.
Kind of like
So-
Greenville.
Is it quite, yeah, I don't know, it depends on the well depth at Green Bluff.
Well, it's all basalt.
It's all basalt. Well, yeah, the wells go through the basalt and into the sediments underneath. So it's anybody's guess what's there.
Well, yeah, nothing, we
Yeah.
had it done because we had to see the county.
Did you?
There's nothing that's straight from basalt.
The limitation with resistivity is we cannot apply it where there's a very thick shale section, because the shale actually blinds the resistivity readings. And I've tried, and it just doesn't work where you have very thick shale sections. So you have to be an area that's very thin or no shale, and other kinds of rocks. If you have just one rock, that's really the best. One rock like this that's fractured, and it's just easy to interpret the data. Okay, next. So this was on Barb Tarbert's property. So I'm going to show two profiles on this one. But to start with, he had two wells here. This well was drilled to about 500 feet, and it was almost completely dry, didn't produce any water. Here's an older well he had that produced water during the springtime. So he said I could start on this golf course here and run up the valley in two directions. And so there was a little divide in between the two valleys. So here are the two sections. And so we have the surface blue. Of course, that's due to the soil water, so we really ignore that. And so this is the eastern profile, and again it's south that direction, north here. So we found this blue area right here at about 100 feet, and on the profile to the west we saw the same thing, but it didn't have the right resistivity values. So we chose that this is the better target, and he drilled that, and he had water shows even starting up here, and eventually completed that for an 8 gallon per minute well, and so he made a garden right next to it. So it's nice to have your own well drilling rig so you can just do that. So then just kind of like to look a little further, the dry well he drilled was right there. And you can see it's all the orange and red color, so that was really hard rock, so that explains the reason why it didn't find any water there. That's about all I know. The other thing I wasn't mentioning. Let's go to the next slide, because at the surface, See, Bob and Mike are standing on this knob right here, somewhat rounded. This knob turns out to be a lava-type rock called an andesite. So the green here is the andesite. And so the andesite was concealing the granite below that. The granite had been weathered. And that's the reason probably that the water was here. So this is probably a weathering surface that was probably exposed for millions of years before the andesite lava flowed over top of it. So it was weathered enough to create just a small aquifer, and that's what he was able to find for his garden. So the well is just about 100 feet to the right from where Mike and Bob are standing, so probably over in this area is about where the well was. Questions on that? That's the second one. Yeah.
Will that water source go dry? It looks like will it keep refilling? Is that all that's there?
Well, that's in a valley too that's charged from upstream.
Oh.
So it's really, again, it's a really good situation because water, even underground, flows downhill. So you could depend upon that. So it would probably continue to recharge. So next, we're going to talk about seismic. So this is not the seismic that's normally used in oil and gas exploration. They use the reflection, and this is called a refraction. And you're probably familiar, if you're a fisherman, with refraction, or especially your grandson that sticks their pole in the water. You notice that it's not straight under there, it's bent up. Well, what's happening there is the light rays are refracted as the light goes from the air into the water, and it bends them. And so that's exactly what's happening with the sound waves here. The sound is refracted, and so we're going to take advantage of that. So here's a neat little diagram that gentleman made. It shows what the motion is on a P wave, the compressional wave. This is the one we're most concerned with. This travels really, really fast. It's not a real high energy wave. When the earthquake hit my house about 15 years ago that went off on Green Bluff, it had the S-wave motion up and down. It just banged my garage door. I thought, God, the garage door fell on the ground. Because that's what it sounded like. Okay. So here's the old type seismograph. This is a 12-channel seismograph. You have to have 12 geophones displayed out along a line. So use the sledgehammer as a source, and then you can go channel by channel and look at the signal in the little TV tube. So that we did away with those about 30 years ago. I'm going to go through just a few slides here to show how refraction works. So we're going to start with just pretend we have a layer here, layer 1, that's 1,000 feet per second velocity that sound travels through it. And layer 2 at 5,000 feet per second. So I'm going to show you how the wave comes out on a diagram, because we can plot the distance to each one of the geophones against the time it takes for the P wave to arrive at that geophone and be read. So we start here after the hammer source is made the sound wave. The sound travels this direction along the surface, and it travels downward here too, but it travels really in all directions. So once it gets to this layer, then it's going a lot faster. It's speeded up 5 times to the 5,000 feet per second. So right now the red dots are just seeing the surface wave arrive at each geophone. But finally at this point, this signal is arriving here first before the surface wave, so we plot it up there on that time distance diagram. And so we just continue like that. And finally we get something like this. So a few years ago I had to do this. I had to write all the numbers down on a pad and then put them on a graph and read this. So there's a lot of information here. The slope, the inverse of this slope is the velocity of layer 2, and the inverse of this slope is the velocity of this one. And then apply those to that little formula, and we can get the depth to the second layer. That's the fast one at 5,000 feet per second. So enough for the beginning course. So here's some examples. I'm not going to go through those. So this is the new data, new equipment. So we have the geophones that are the same as before. Here's the sledgehammer, the seismograph, the yellow device, geophones, there's 24 of those. Then the cable right here. So we spread the cable out like that, 24 at a time. The seismograph here, they're usually spaced at 5 or 10 feet between geophone. So when we get a data stack that looks like this. So this is a raw data. So what our first job after we get the data is to plot the first break. So this is the point right here where the P wave arrives at geophone 3. But to get one of these, we have to start by a hammer strike here to get the first record, and then we do one here and there in order to determine, well, how far off end does this hammer strike have to be, and the same for that one. And it's important because we need to know this point right here to decide that distance. So then eventually we do either 5 or 7 shots. So we'll get 5 or 7 data stacks just like the one on the lower right. Here's a picture of how the equipment's deployed. What's that?
Each time the sledgehammer comes down is one shot?
Yes. Well, actually what we could do, if we have a long line that goes beyond 240 feet, so we have 240 to 480, we have to take several shots at the same point. Now the seismograph can accumulate each of the shots, so you could get a better record. And that's important when you get over about 200 feet. So you usually have to have at least 3, and so if you're well over 300, you have to have about 6 or 10 strikes with a hammer. So nobody moves between the time you say, go ahead, help her hit the ground with a sledgehammer. So you don't dare move, otherwise you're going to mess up the shot record. Yes?
When you're looking for the point of refraction, when you hit that point, is there a signal of some sort?
No, you have to look at the shot record like I showed in the last diagram.
Because you need that point.
You need that point to know how far off end to set that off end shot on both ends for reasons that I'm not going to discuss. Just need to know that. Was there another question I missed? Okay. So next. So we're going to look at this a third example. We're not going to have any resistivity data here. This is another farm in Lincoln County. The farmer's got an old windmill here that he now has a submersible well in. So we had our seismograph line laid out here. So he pumps water from there up to a cistern in his house. So I don't have a shot record here, so this is the interpreted profile. See, the software assumes that you have 4 layers, and so it just makes a simple interpretation, but it's usually quite good. So what I already knew here that we had just granite in the area. There was no basalt. There may be weathered layers, and so this diagram is showing us that we have weathered layers. So we have the soil zone here, and then a very well weathered granite, a little less weathered, and then a very hard granite here. So here's the well, static water at 25 feet. So we can just interpret that the water mostly is coming from the orange and the green layer. And there's probably not any storage in that purple layer, which has a velocity of 8,800 feet per second. And that's about all we could learn from that one. Although I think I did, another model. That's more or less what I said. That most of the water storage is in these 2 layers right here. So if this farmer would have pumped that well continuously, maybe he had 2 or 3 sprinklers, you probably would have run it dry for a time. It wouldn't have been able to recover because there's just not enough storage in those water zones to sustain it very long.
But if you had drilled the well at that end of it, you would have had more.
Yeah, probably, right. Of course, we didn't run the section over the well, so I'm not sure what's present there. But this house has been there for 140 years, so it's at least has had enough for the purposes that they needed for livestock and just a little bit of lawn watering. So yeah, there's a lot of things you could think about. Should we extend the line over the well? Should we go in a perpendicular direction? So you can learn a lot more about it if you did that. Okay, now combination methods. So this is another northern Lincoln County site. Here's the county gravel pit. The seismic and resistivity lines were run right there. Resistivity line is in red. And so I'm showing the resistivity profile. So again, I knew I had gravel at the surface and I didn't know how thick it was. And I was thinking, well, maybe there's some water below. So we learned from the resistivity that there's a 20-foot thick gravel layer and then a water zone here that's another 47 feet. So, but I didn't know what the rock was in the blue colored area. So, is it granite? Is it basalt? What characteristics does it have? So at this point we ran seismic. So here's 2 seismic shot records. The first shot records was here, number 1. And so here it goes into the second layer. So you can see this record going up and it changes slope right there. So we're into the second layer at that point. And the same one here, but it gets to the second layer about this point. What I noticed about this one is that there's a very shallow slope on these I guess they're called first break picks. So that suggests that this rock is very hard because it has a high velocity on account of that very low slope. So right off I suspected that it was a basalt. So here's the profile, and sure enough, the velocity in the lower layer was over 15,000 feet per second. Then we had this dish-shaped area here that I don't know really quite what it is. Then we had the 20-foot thick gravel layer that was a very low velocity. Then we went one step further. There's a second way to model the data, and that's called by this thing, the tomographic model. And it has an advantage. We can assign as many as 10 layers with different velocities to the tomographic model. Well, I didn't have that many, but it was a good exercise to see what it was. But generally it gave the same thing. We have this dish-shaped area. The red lines show where the seismic survey was run. So we have about a 12-foot gravel. Goes into a medium velocity zone, which is probably a basalt that's fractured, and then into a very dense unfractured basalt. So this section right here is the yellow and the green. So from this we could conclude that this is a basalt, and it's fractured, and the fractures hold the water. And that's the end of that one.
Water, something like that, would be 10% or 90%?
I don't know. Maybe I would think it would be less than 10%. Actually, yeah.
Once it was dry, the pocket was sinking.
Yeah. I'm not sure what it would be. It's fractured rock. There's a lot of the pore spaces are connected, so the water has the ability to flow rapidly from one spot to another. But what the pore space is, I really don't know. Okay, and then here, this is the final model. So I just showed the basalt as broken with fractures with this symbol. And so it's fairly simple, like that.
So,
That's-
what were you doing that to determine how much water was underneath the gravel?
We didn't know how thick the gravel was because, well, we were really considering selling the gravel to the county. And wanted to know how thick it was. So to know what's beyond the gravel was unnecessary. But it was, a good learning opportunity to know that it wasn't gravel below 10 feet.
Drill, let's say somebody wanted to drill a well, would that be
Yes,
where you could actually successfully get water?
yes, should be able to.
Okay.
Do you have a feel for what kind of success rate you have for wells drilled by for your?
Analysis?
No, well, the ones that I know about are successful. I take that back, these techniques are not perfect, and I want to emphasize that.
The odds, I just,
This is an interpretation based on my experience using that data. So if people using this information say they know what it is, what they're doing all the time, well, they're not being truthful.
can't guarantee it.
No, we can't guarantee
I
it.
understand that, yeah. Just
There's
have a feel for your success rate.
Yeah, we have some targets that are identified, so we try to use or to eliminate all the possible errors in doing that. That's why I mentioned earlier that the shale is a problem area, so I stay away from those areas. So we're going to talk next about the third method, and this has to do with some equipment I bought last year that was used by a gentleman in Walla Walla for about 10 years, so I can't take credit for his work. So, but the way this works is, and this was the first textbook that's ever been published on the Seismo-electric method, just published in 2015. What happens here is that the seismic wave, seismic shock wave goes down, intersects a water zone. The water zone makes a battery effect, and this battery or self-potential effect has been known for more than 100 years. That battery effect creates a very small current, and then that current is read at a receiving station. So once a current's generated, it travels at the speed of light back to the surface. So because it does that, we need to know the composition of the rock between the water zone and the surface, so we can estimate the depth, like we did on the seismic data that I just showed you examples of. So that way we can tell the depth of the water zone. Next, so this is what the equipment looks like. It's really simple. So we have the buffalo, and over here it's buried in the ground about 3 feet. I have to use a power auger to get it in the ground. Then there's 4 electrodes for the antennas, a computer that does the recording, and then we put a shotgun shell down in the bottom. So we use a 3, 6, or 9 dram load. So a normal 12 gauge is a 6. So sometimes when we have a water zone that's very deep, like 1,300 or 1,500 feet, we want to use the 9 dram load. And we get good results on that. So there's the other wires, and that's really all there is to it. So, but the disadvantage of this is you get data from just one point at a time. So we call this a sounding method. So we have to do several soundings in a row to make a profile. Usually you can do 12 to 20 of these in a day. If it's a long day, maybe a few more, and so on. So, well, I mentioned the concept there. Phenomena has been known for about 75 years. And other like phenomena are the self-potential or streaming potential, which is the battery effect. And yeah, soundings 12 to 20 per day. use a 12 gauge shotgun shell, and then I showed the equipment. Range, to about 1,300 feet. So I'm going to show kind of a layout here how this works, kind of like the seismic. So we start with a seismic shot wave at the surface. So the seismic shot propagates down, creates the electric dipole called the Seismo-electric conversion, where the seismic energy is converted to electrical energy. And then that's instantaneously transmitted back to the surface. And that's how it works. So this diagram, I think, was supposed to be an electrical image of this seismo-electric transformation. Okay, so here's a typical record. So we get data, we get a hydraulic conductivity chart. Hydraulic conductivity is the velocity that the water's moving. And then we get a voltage chart. So we got two channels, so we have two chances to get it right or get it wrong. So the kind of, we're looking for kind of a bell-shaped curve like this, and so we could say that this is the bottom of the water zone, that's the top. And so we look for confirmation over in the hydraulic conductivity, and in this case it's showing it that they at least show the same information. So one's confirming the other. So we can say there's the water zone. But the one thing I mentioned again, it's very important to know what the velocity of the rock is going down to this point. We need to know if it's 1,000 feet per second or 5,000 in order to estimate the proper depth here and there. That's important. So the next slide. So here's a record that he recorded near Grand Coulee. So we have eight records set up in a profile. So we come up with an upper aquifer and a lower aquifer, and then some records in between that are uncertain. And from those we can actually estimate the flow that you would get if you're drilling a well. That's the advantage of this. So it gets really good data, but it's just one point at a time. One sounding. Here's some data that I recorded last year. So again, we have the bell-shaped curve. I didn't get good data on this one, so I shot the second one. Didn't get the second channel. And this one was too low of energy or something like that, but it still was good data. I was surprised. So from that we can estimate the flow from each of those zones. So we have a surface zone at 45, several thin zones, 16, 10, 10, 12, and 6, that if you completed those by themselves, they might be enough water. But if you completed this whole zone right here, it would be much larger, 116 and 62. Then on the next point, which was about a quarter mile away, somewhat similar, still had a surface zone. Then this long zone is 124 gallons a minute, which I was amazed to see that. Okay, I think that was all. And then this diagram shows 4 years of his surveys over the 3-4 state area, and they're color coded by gallons estimated that would be produced in a well. The best one is over 2,200, and he said that one of those estimates of 2,200 actually came in at 3,000 gallons per minute in an irrigation well. So, and I don't have a lot of data confirming the readings he took with the actual well drill later on. So I really can't comment on that, except for that one example.
Question.
And
So you
yes.
can estimate the amount of gallons in the aquifer.
We can estimate how much the water would flow.
If we had 1 trillion gallons, let's say, available, you can estimate by combining methods here how much water there actually is.
Yeah, somewhat. We have to have more information than just the flow.
Maybe on both sides.
We need to have the dimensions of the aquifer too. So usually if you have enough profiles, you can estimate that, right? You need to know the boundary of the aquifer, both vertically and horizontally.
You get the volume of the
Right.
outline.
You generally have an idea what the pore space is in the rock. You know, it's generally around 10%, something like that. Anyway, I think that's it. So this is my Rube Goldberg method of measuring water levels in a well. So for about $50 at Lowe's, you could put one of these together yourself.
Wow.
So you have,
How much is government calling you? Dave,
the
what
government
water
doesn't,
is-
they don't, well, the people with ecology think they have all the answers, and so they don't call me. As you will hear from John Colbert on Tuesday. Because I was against him at a hearing one time, and everybody listened to ecology and didn't listen to me. So all this is I brought up a 5/8" bolt, speaker wire, a couple alligator clips, an ohmmeter, and then a reel. So you just drop it down the well, look for the first indication of a current coming in the ohmmeter, mark on the cable, the speaker cable, and pull it out and measure from that point down to the bolt, and that's the depth of the water. So that's it. That's all I have. Any questions? Yeah.
The depth of the reservoir?
Well, we're measuring the water level in a well.
Right.
Yes.
Right in the reservoir of the 6-inch diameter drill.
Yes,
Yeah.
right.
The bottom.
So, you know, it's kind of, if you have your own well, you might want to know what this is as the seasons go by. Does your water level drop? And how much does it drop? That would be good information to know, and so you can kind of gauge your use based upon that information. You can come by.
Dropping the float in.
Oh, yeah, you could do a float, but this is, you know, the bolt goes down in the water, and so you don't know when a float would actually intersect the water.
Well, you just put a plumber and listen for it.
Yeah. Gloria?
Dave, could you send that to us via email or something?
Yes.
That last picture.
I could just send you the whole thing. If anybody wants any of my talk information, you know, put your name up here on something, and an email, I can send this talk or the Avista one, so you can see everything that Barack Obama was involved with. And you can find hundreds of articles about what I told you about in that last slide. Yeah, yes.
Do you wish to comment on the use of wire and
Dowsing.
sticks?
It's magic.
Down.
Dowsing is just, you know, your level of religious belief in that method, I guess. Yeah, okay.
Let's give Dave a really
Okay.
good.
Yeah.
Thank you so much. Good
Okay.
information.
So anybody want any copies? You're welcome to it.
Something that's totally silly and sidetracking your spare time. The Seismo battery effect.
Yes.
Have you ever thought about applying some of that theory to the Giza Plateau and the pyramids?
Oh, no, I don't want to.
That's kind of a wild theory.
It's too hot there. I don't want to go there.
But the water flow under the pyramid and the fluctuation.
Is there?
They're trying to make some theories that, yeah.
Well, they can use this method there.
Generator.
Yeah, they can use a lot of geophysics there. They just use the very shallow geophysics that I've seen so far.
Energy's available.
It only goes to about 20 feet. You know, this information you get to 300 feet perhaps. Yeah. Yes.
Do you ever expose gophers, worms, animals come up with any of this?
Oh, I'm sorry.
What?
Well, I was just going to say, there was one more announcement before everybody starts